All right. Sorry that I just set up the live on the YouTube channel. So can everyone see the slides?
Yes.
Okay, great. Thank you. All right, I think it's time to start. And so first, I want to remind everyone that our homework 0 is due on this Friday. On May 9th, I guess it's 11:59. So if you haven't started doing that homework, please do so right away. And also, it's good. It's good to refresh your mind and with this basic knowledge. And also, I'm happy to see many students have already started that, and I see like active discussions on Piazza is really good. And so let us keep building this active learning environment. And again, please take advantage of our office hours every weekday. So if you cannot make it for any day, like just you can switch to another day, or you can you can request our TMs to say if we can schedule another time to meet. Okay, so and also thanks for your patience to like spend about 2 lectures to walk through the whole schedule, the syllabus, the logistics, all kind of steps. Hopefully that'll give you a good foundation for you to make decision. So today we're gonna first quickly review the basic knowledge, which are covered in homework 0. So hopefully that will be helpful for homework assignment. And then we'll look at the setting of supervised learning framework. And then we'll talk about our first machine learning models called decision trees. Okay, so let us start with the basic knowledge review. And we'll give a quick review of those basic concepts just for your reference, but it's not, it might not be good enough for you to address every problem of your homework 0, right? So if you still have problems, then try to locate the knowledge points, your textbook, and also I have a shared one online book in our Piazza, and also in the course webpage. That is really a good reference for you to quick review those concepts. If you feel like your previous book is too thick or too complex, right? Okay, so we'll first look at the definition about random events and probabilities, right? So we know that the randomness are ubiquitous in real world, right? So, but mathematically speaking, how can we define random events, right? So we use sets, right? We use sets to represent random events where each element in the set represents an atomic outcome of your random experiment. Like your example, like your experiment is to toss a coin, say for 5 times, right? Then we can define an atomic outcome will be just the result for 1 tossing, right? So then we can look at the set of the tossing results, right, which define the events, right? So one event will be, okay, you toss the coin for 5 times, you end up with 3 heads in the first 3 times and 2 tails in the remaining 2 times. Okay, another event will be like you first have like tail and then head and tail, right? So you can define many events, right? So we want to measure the chance that each such kind of event happens, right? And this is chance zero called probability. So that means we have to define a function that maps this event set to represent to some kind of value between 0 and 1. This is called probability, right? So we usually represent as P of A, right? Meaning the probability of event A happens, but A is a set, and probability of B, right? And a very convenient nature of this such kind of definition is that because we know set operations, right? All kinds of set operations, by combining set of operations, we can create more diverse and complex events, right? Say basically, given the definition of event A and B, we can define a new event that both A and B happen. How can we do that? We just take the intersection of A and B, right? And a fourth event can be defined as A happens or B happens, right? So in terms of set operations, this event is represented as the union of A and B, right? So maybe I'm saying this equation in your probability book, a statistic book, long time ago, right? So the probability P of A union B equals to P of A plus P of B subtracted by P of A intersection with B, right? So someone asked me last week, right? How do you show that P of A union B less than or equal to P of A plus P of B, right? You just list this equation. That's it, right? So of course, I mean, most statistic book or probability books will give a general version of this. Like suppose you have a bunch of events, A1, A2, A3 to AN, right? So how do you calculate the probability of the union of these n events? So there's a general equation. So you can see it's kind of alternating summation, subtracting, summation, subtracting. So if you're interested, you can just find a book or check out the Wikipedia page. And a very intuitive investigation or visualization of those events is through the Venn diagram, right? So everybody has heard of the Venn diagram, right? So I just showcase that if you in case that you you forgot, what is it? So can everybody see the whiteboard? Is it clear to everybody? This is a whiteboard. Okay. So what is Venn diagram? What?
I can't see it.
Okay.
It has not displayed yet.
It does not display?
As of right now, it's not showing up. It says
that you started sharing your screen, but we can't see your actual screen yet.
Can you see it now? Okay, let me do it again. That's the first time I use whiteboard. Can you see the whiteboard now?
There we go. Yep. Mm-hmm.
Yep.
Okay, nice. So so we can use a circle, right? A circle to represent the event, which is a set, right? So this represents event A, right? The area of this circle is actually the probability of A, right? And another event could be like this, right? Event B, right? This is a probability. So the probability of A happens and B happens, right? Jointly, A and B joint happens are represented by the intersection of A and B, right? So forgive my bad, awkward drawings. I'm using the mouse to do that. Okay, and then what about the union? You just look at the area where both A and B occupies, right? This is a union, right? P of A union with B, right? So obviously you can see that if you want to calculate P of A union with B, it is equivalent to summing P of A plus summing B, and then subtracted by the overlapping part, which is P of the intersection of A and B, right? That's where the equation we just mentioned come from. Right? Of course, if you have like multiple events, right, you have multiple sets overlapping, and you still want to calculate the probability of their union, you have to use more complex operations. You have to sum up the individual probabilities of each union and subtract it by their pairwise intersections, and then add it back their triple-wise intersection and subtract it by their false unit. Those kind of things, and until you reach the I guess it's a union of all the intersection of all the sets. Right? So it's kind of like a long equations, but it's really provided by a standard textbook. Okay, so let us get back to our slides. So does everybody see the slide?
Yes.
Okay, great. So so this is the definition of the concepts about events and probabilities, and then an important extension will be random variables, right? So what is random variables? So the motivation of random variables is for the convenience in the research and rigorous study about those random events, because if you just talking about everything under the sets, it's not that convenient, right? So the most familiar things to mathematicians or researchers are just numbers. So the random variables are using numbers to represent the sample outcomes or experimental outcomes. So and then we can represent the events by, say, describing some random variables following some region. Right? So here I'll give you a concrete example. Like again, suppose our experiment is to toss a corn, right? And we now introduce a random variable x to represent the result or the outcome of our experiment, and x equals to 1, meaning okay, you have a head up, right? X equals to 0 means you have tails, right? So if we toss a corn for 5 times, then we have like 5 random variables x denoted by x1, x2 to x5. Right? So now we can use some kind of mathematical inequalities or equalities to represent all kinds of events. For example, if you want to define the event that we obtain 3 heads out of like 5 tossing experiments, we can represent these events by the inequality x1 as x2 through x5 less than 3, right? The reason is because when x is tail, the value of x is 0, right? So the summation, it doesn't take any effect in the summation, right? And then the probability of such an event is the probability that this inequality holds. So that's the most frequent ways when we talk about modeling and the estimation, those kind of stuff. Right? So hopefully this will kind of like raise your help you recall those concepts. But rigorously speaking, random variables are not just numbers. It's essentially a mapping from the original outcome space to some real space, and this mapping must be measurable, meaning the image, the inverse image must be onto some sigma algebra. But this is not required to for everybody to know. But at least we need to know why we introduce random variables, right? And how we use in mathematical inequalities to represent all kinds of events. Okay, so then given the definition of the random events and random variables, and then we can talk about the probability, right? The probability that multiple events happens, right? So we call it the joint probability, right? So the joint probability of two events happen, A and B, is defined as the probability of A happen multiplying with a conditional probability, that is B happens given A happens, right? And symmetrically, we have like this joint probability equals to P of B times P of A given B, or condition on B. Right? And we have a similar definition for random variables, right? The joint probability of two random variables X and Y is P of X, the marginal probability of X multiplying with the conditional probability of Y given X, right? Or we have another symmetric definition. So, sorry. We can extend this definition to many random variables. Then we have a sequence of product, right? P of X, P of X1 times P of X2 given X1, P of X3 given X1, X2, and so on, right? This is called the chain rule for the probability, or the full probability formula, right? So another very important and extremely important concept is called independency. So I want to know that in what kind of circumstances two random events are independent of each other. Right? Intuitive speaking, independence means that the occurrence of event A has nothing to do with the occurrence of event B, and vice versa. Right? And how do we give a mathematical definition? Right? So here's the definition. So if the joint probability of two events A and B equals to the product of their own probabilities, namely P of A times P of B, then we say A and B are mutually independent. And also, and again, we extend this independency to random variables, right? We say two random variables X and Y are independent if their joint probability is the same as the product of their marginal probabilities, respectively, right? P of X multiplying with P of Y, right?
What's the difference between joint probabilities and the intersection between two,
that's a good question. Actually, joint probability, you mean the events, right? It basically says that P, A, and B is actually P of A intersection with B.
Gotcha. So they are equivalent. So P of A intersect B is the same as P.
Yeah, same as. But really, I mean, your textbook or your notations, we just use A, comma B to represent A union with B, because comma looks easier to write, right?
Gotcha. Okay. Yeah, and it's intersect, not union, right?
Not union.
Cool. Okay.
Any other question? Okay, great. So we can extend the concept of independency to be among like multiple random variables like A1, A2, A3, A4, A5, and so on, right? So the definition of independency is the same, right? If we say a set of events A1, A2 to AN are mutually independent, meaning that their joint probability is the product of their individual probabilities. Like the same definition applies to random variables. Okay, so if we contrast to the mathematical definition of independency with the definition of the joint probability, we can find another definition of independency. Right? So we see that because independency entails that joint probability equals to P of A times P of B, right? And in general, no matter A and B are independent or not, P of A and B is always equal to P of A multiplying with P of B given A, right? So now, if we compare with the two product here, we can see that this marginal probability P of B is equal to the conditional probability of B given A. This gives us another definition, meaning that the independency also means the marginal probability is equal to the conditional probability. Right? The B happens or not, even the B happens or not, it's nothing to do with A happens or not, meaning that the marginal probability of B is the same as the probability of B given A. Right? So these are most common used definition of independency. So everybody, when we talk about independency, is some kind of like reflexive response, right? We're going to write down this joint probability equals to the product of individual probabilities. But sometimes it is more convenient to think in that way. Like the conditional probability, if the probability of your events, right, or random variables is equal to your probability of events, the same events in random variables, conditional on other random variables, it means that, okay, your event or random variable are independent to that events, because conditional on that or not does not change the chance to happen. Does it make sense? Is everybody happy? Yeah, hopefully that'll give you some kind of a good refresh of your what we have discussed your statistics class and probability class, right? So we can also extend independency to the conditional independency. Basically means that if condition on a third event or random variable, whether the two events or random variables are independent, right? So again, same definition, right? We claim that A and B are conditionally independent given C if this P of A and B given C equals to P of A given C multiplied with P of B given C. Okay, so given the random variables, we can look into many of its properties, right? But one important property or characteristics is called expectation. So expectation simply means because the random variable is kind of unstable, right? It might be here, it might be there, right? So we're interested at on average where it shows up, right? So this is called expectation. How do we calculate expectation? It's integral. So the integrand is the random variable itself and the probability of these random variables, or probability density of these random variables, right? So you can view that as kind of weighted summation, right? Weighted summation of different values that this random variable can take, weighted by the corresponding density. Right? So if our random variable is a discrete random variable, then this simply becomes a summation, right? And the expectation can be extended for functions of random variables, right? So if I'm a function g, and we want to look at, and then the g of x is another random variable. So remember, if your input of a function is random variable, then your function is random variable as well. So g of x is another random variable. If we want to calculate the expectation of g of x, we do the same kind of integral. And integrand is g of x and the probability density of x. This is our definition. Hopefully, you follow this definition to calculate the required mean of variances in our homework problems. And I think the second most important the property of random variable is called variance. Right? So variance basically describes how far away you jump from the mean or expectation. Right? So the definition of variance is the expectation of x squared subtracted by the square of the expectation. So can show that the variance is always non-negative. Okay. So if you're interested to show that, please do that. I'll leave it as a practice for you. It's a good way to recall the basic concepts and definitions. Right? So those variances calculated with x is a scalar, right? It's a number, right? But in many cases, right, especially in machine learning, we in general view x as a vector, right? In that case, we're not only interested to calculate the variance of each element in this vector, we also want to calculate the so-called covariance matrix. So covariance matrix describes not only the diagonal part of this covariance matrix, describe the individual variances of each element, but off diagonal parts represent the correlation, statistical correlations between different elements in this vector. Right? So the definition is similar, but in a matrix vector form. It is expectation of XX transpose. So it's the outer product of the vector X. So it becomes matrix. Then subtracted by the outer product of the expectation of X. So EX transpose. So again, we can show that this covariance matrix is always semi-positive definite. So please be aware if we're talking about matrices, and if say if a matrix is bigger than, is greater than or equal to 0, that does not mean its elements are greater than or equal to 0. It just means it's semi-positive definite, meaning that all eigenvalues of that covariance matrices are non-negative. And then again, we can generalize the idea of the expectation variances to be the conditional expectation variances, right? We can calculate the conditional expectation of x given y and conditional variance of x given y. Right? So if we calculate conditional expectation, then we should replace the probability density here by the conditional density, namely P of x given y, right? And similarly, when we calculate variance of conditional variance, when we those expectations are all under the conditional distribution of conditional density. So now I want to ask a question. So we know that because the expectation are kind of marginalizing out the random variables, so expectation is a scalar, is a constant. It doesn't have any randomness. So now I want to ask, is conditional expectation of variance also constant?
If I understand it correctly, I don't think so, because I think it's the expected value of x given some random variable, and so that y is still random, right?
Yes, excellent. Very good answer. This is very, very important. I think it's a good checkpoint to see if you really capture the definition, right? Yeah, you're right. So because the conditional expectation is computed based on the conditional probability density, right? X given y. So when you calculate conditional expectation, this is essentially depends on the choice of y, right? So when y equals to 1, you have one conditional expectation, right? When y equals to 2, you have another conditional expectation. So this is essentially a function of this random variable y. Just as we just mentioned, right? A function of random variable is another random variable. So the conditional expectation is actually a random variable. That's why you have seen that seemingly weird problem in homework 0, right? Requiring to show that you take expectation again after you take conditional expectation, then you will get the expectation of x. So similarly, conditional variance of x given y is also a random variable. It's not constant. Okay. So those are about like very important concepts about probability, right? you need to know what is the random events, what is the random variables, y random variables, expectation, variances, and independence, all those kind of things, right? And the next thing we want to discuss is about the definition of convex functions. It's very, very important. It's kind of a central role in modern in machine learning models. So convex functions are defined on convex regions, or convex set, or convex domain. So what kind of domain, what kind of set can be seen as convex, right? So basically, if in your region you random pick up two distinct points, right, and you can draw a segment between the 2 points, your whole region is convex if and only if any point on this segment still belong to this set. So now you can see, like, you can pick up any arbitrary 2 points in this set, right, and then draw a line, draw a segment between them, connecting them, and you will see any points are still on this segment are still inside the convex region, right? This is called convex. Basically, if you want to satisfy this property, the geometry of your set must be outward. If you take a look at another example, this is a counter example, right? This is not a counter example. This is not convex region. It's not convex. Why? It's not convex region. If you pick up a point x here and point y here, if you draw a line segment, you will see all the points in the right part here are outside of the region. Right? So it's Kinney-like region definitely is not convex. So you see there are some kind of part are going inward. So that's the definition of a convex region. So convex function is mapping from a convex domain to real space. And but we have some actual constraint about convex function. We require that for arbitrary points, arbitrary 2 points in your domain, right? And if you choose an arbitrary point t between 0 and 1, we require that the function evaluated at this linear combination of x1, x2 by t, right, is less than or equal to the linear combination of the function evaluations at x1, x2.
Professor, just a quick note. I don't think your slides have updated for us if you're drawing on them.
Can you say it again? What's the problem?
If you were writing something out, or if you have changed slides past the region slides, then we are not seeing that update.
I'm not drawing on the slides. I'm just moving the hovering the mouse. Did you see that? No.
I personally have not, but I don't know if any of the other students have.
I'm not either.
So when I move to another slide, do you see that?
No, we are not seeing that.
Oh, it's horrible. Why Zoom is working horrible today? Let me redo the slides. Okay, I'll redo the. Sorry about that. So can everybody see the slides now? Okay, yes. let me play it. Let me play it. So is it good? You see the slide? Okay.
Yep, going now. Thank you.
Okay, no problem. Yeah, just interrupt me, stop me when we have any issues on that. Otherwise, I feel everybody is look at the slides and feel comfortable. I don't want to talk to some empty slides. I mean, from your side.
I also, for the record, don't think we can see you when you hover your mouse. I'm not sure if that's. Oh, now I can. Yeah, never mind.
Okay.
Yep. Okay, nice. Just making sure.
Okay. Yeah. That's great. Looks like we have sometimes if it's problematic, I have to stop the sharing and reshare the slides and then play. Okay. Did everybody miss the definition of the convex set or convex region?
If you could quickly
Yeah.
go over it again really quick.
Okay, yeah. So convex region basically means that the set, geometrically speaking, is kind of outward. Right? So you cannot have any part inward. Like more rigorous definition would be like if you pick up arbitrary 2 points in this region, and if you connect the 2 points, then all the points on this connecting segment must be inside the region. Then we call it convex set or convex region. And a negative example is like this, right? So if you pick up 2 points on the 2 ends of this kidney shape, right? So if you connect them, you find that this right part, all the points on this right part actually are outside of the region. So this region cannot be called convex. It's not convex. So that's why we have to. I mean, geometry speaking, we have to ensure that your shape of your region of your cell is kind of outward. You can never have any part like going inward like this.
So
Okay.
what are these sets representing? Is this like an object with an actual shape, or is this like a probability space, or what is this describing?
Also, it can be any set you're interested in, because we're going to define a function, right? A function is mapping from an input domain to some other output domain or range, right? So if we want to talk about convex function, we need to ensure the domain is convex. But regarding what's the meaning of your domain, it depends on your application, your problem, right? So suppose I want to learn some kind of function or probability, then your convex set might represent all possible experimental outcomes. Right?
Gotcha. I guess I'm not drawing the connection between like whatever you can represent with an actual shape of that, right? Like with the Venn diagrams and things for probability, their shape doesn't really matter. It's all about like, can they overlap or not, right?
Oh, yeah.
Where if this is a domain, right, like what determines its form at all? Is it like values like XY coordinates on a plane? Is it like, and that's what gives it its shape as a region?
Oh, no, we have this is not about talking about some function values on the points on this region. It's just talk about the property of this region itself. Of course, it has nothing to do with Venn diagram. Venn diagram, like you can draw a even set like this, right? It doesn't matter because Venn diagram just want to show the relationship between different events, right? But here we just want to look at the property of this single set, and some special family of sets called convex. They have some common property, which is called convex, meaning that if you pick up any 2 points in this set, and all the lines, all the points on the line segment connecting the 2 points must be inside this region. This is called convex. And I want to define a function where the input domain is a convex set. This is where convex function comes from. But you don't need to make a more sophisticated connection between, say, those convex regions and other things, like probabilities of even sets, or this is nothing to do with even representation.
I kind of understand that those are very different things. I guess I still don't understand what we are representing by X and Y in this case, because it's like, all right, you take X, you take Y, and you draw a line between them. But like, what does that mean? Because I can see like if X is a coordinate and Y is a coordinate, you can draw a line between them, right?
Yeah. Let us view it like in real space. So you can view X and Y are just points, points in the coordinate system or Euclidean space.
Got it. And so like that would be an example of something that would have like a shape, right? If I had a set that's just say all real numbers, right? Like what shape is that? How do you even define that as a shape? Is it just a straight line of zero width? Like
Then you don't have shape on that actually, because the shape is because
right.
the set is not closed, right? It's unbounded.
Okay, got it. So like I guess that kind of hints us to the answer, because I'm just wondering, like, we have sets of things, right, which you can think of just like, points of data, numbers, right?
Uh-huh.
And like, how do you go from that to actual shape, right? Like, how do you get it? How are we transforming them into a visual representation in the first place?
So you're saying that you have a set of data points, you want to see their shape?
That's, I guess, like that's what I'm wondering, if that's what's happening here.
Oh, it's not happening here.
Okay.
Yeah. I mean, we haven't talked about like specific machine learning problem, right? You have a set of training points. I want to say how those training points are distributed or located in some space, right? This is a very interesting problem. This is actually finding the structure inside those data points is kind of a key problem. It's called unsupervised learning, right? But here we just give some mathematical definition. Right? If I want to, we're talking about like point sets in real space, and I just give you the definition. Like what kind of set
so
called convex?
I think what he's implying is, how do we go from sets like points to a shape, and that probably is like how the function is defined. So we can assume that the convex set is a circle, then that circle will have a definition of x square plus y square less than equal to r
Oh,
square.
uh,
Am I? Is that what you were going for? And then we can prove that that set is convex. Like with that function actually implies that these many points will be equal. Like these many points will be in this set. And how do you prove using this? Did that make any
I think you
sense?
did definitely latch onto my core question there. I don't know how relevant it is to the actual coursework though. So if we want to move on, we can, and I can just talk to you in office hours or something.
Yeah. I think this is beyond our. Yeah, of course you can define shapes. You can describe shapes according to XY coordinates definitely. But in general, let's just put it aside. I just want to I want to introduce the definition of convex. Is no matter whether you have some exact definition of the shape, description of the shape in terms of the points, the coordinates. Okay, so now let us look at convex function, right? So basic convex function, the input domain must be a convex set, as we just mentioned, right? The output domain is really real numbers, right? And we require that for any input that from this domain, and if we pick up any point, any coefficient t, which belongs to 0 and 1, and we require that the function value at the linear combination of these 2 points is less than or equal to the linear combination of the function values at these 2 points. So this inequality must hold for every 2 points in the domain and every possible coefficient for the linear combination. Right? So to give you a concrete example, so this black curve is a typical convex function. So we can examine if this inequality holds, right? So we can pick up 2 points, x1 and x2 here, and then pick up a t. So our linear combination of the inputs stay in between x1 and x2 here, right? Then the function value at this linear combination of input is here, right? This is the left-hand side of this inequality, right? And then we look at the right-hand side of this inequality, right? So the function value at x1 is here, right? The function value at x2 is here. And if we want to calculate their linear combination, right, at t, we just draw a line and then draw a perpendicular line across this pink line, right? We got the linear combination of f of x1 plus 1 minus plus f of x2, right? Weighted by t, right? So you can see that the linear combination of the function values actually is bigger than the function value of linear combination of the inputs. So that's the definition of convex function. So it's a little bit complex, but it actually reflects many beautiful properties. So here are a few examples of convex function. If your input x is just a scalar, like exponential function, is a convex. Negative logarithm of function is convex. So that means logarithm of x is concave. So someone may ask, right, what if I switch the direction of this inequality? Right? If it becomes bigger than or equal to, then we call this function as concave function. Okay. So if the function, we also have like convex function defined for a vector input, right? So one example is the so-called affine function. So A transpose x plus B, right? This is kind of linear function of the vector input, and quadratic function x transpose x, which is convex as well. And you can try to prove that with the definition. And how can we check if a function is convex or not, right? So one straightforward way is to use the definition, right, as we just mentioned here, right? So, but more commonly used test conditions are given as follows, right? So first, if the function is differentiable, convex is equivalent to saying f of x is always always bigger than or equal to f of y plus the gradient of f at y multiplying with x minus y. So by the way, is the inner product. The x, y are chosen arbitrarily from the input domain. So I want to ask, what does the right hand side mean? An idea?
So the upside down triangle symbol, you're using that for differentiation?
Can you see again the what?
The upside down triangle symbol, you're using that for differentiation?
Yeah, differentiation. It's a gradient.
And the t is transpose?
Yeah, t is transpose. This is essentially a tangent line, right? It's the same. This is the same as like scalar case, right? If you evaluate a function value at some point, and then plus the gradient of that function value and multiply with x minus 1, right? X is an input of function. Then this is a tangent line of the function curve. So basically, this include means that the whole convex function must always stay above its tangent lines. Yeah, I would encourage you guys to check this, like to draw some convex curve and their tangent lines, and to verify this fact visually. And another very popular used testing condition is the Hessian matrix. If your function is twice differentiable, and then the function is convex, if and only if the Hessian matrix is positive semi-definite. Of course, if x is just scalar, that means your second derivative is non-negative. So you can use those two conditions to test to prove the convexity of that function given the problem given in the homework assignment. Okay, a very famous inequality associated with convex functions is called Jensen's inequality. Right? So what does Jensen's inequality say? It says that if x is a random variable and f is convex, then f of expectation of x is less than or equal to expectation of f of x. And this can be further extended to function random variables, right? The function f, the convex function f of the expectation of the g of x is less than or equal to the expectation of the function of g of x. So Jensen's equality actually takes a central role in probabilistic machine learning, especially in approximate inference called variational inference. In variational inference, the basic idea, I mean, the underpinning idea is to apply Jensen's equality to derive some lower bound of the model evidence, because in practice, probability models, their model evidence is analytically intractable. You cannot compute it. Then people often seek to derive some kind of loose lower bound, but is with much nicer form, so that we can optimize it and estimate model parameters. Okay, the last thing I want to cover is about matrix derivatives, right? So I believe everybody is kind of familiar with taking derivatives or gradient with respect to scalars, right? But in general, in machine learning area, we are more interested in vectors and matrices. Those are basic elements or mathematical objects, right? Then it requires us to be familiar with the derivative with respect to matrices and vectors. So, but the definition is exactly the same as the element-wise definition, but the operation is kind of a little bit more complex. So here is the suggestion how you take the derivative with respect to for matrices and vectors. Don't try to do it element by element and then summarize into a matrix form. Instead, try to decompose your, say if you have a function of vectors, try to decompose it with the chain rule, and then reduce each component into the atomic rules listed here. Right? So we have like the partial derivative of a constant matrix to be simply 0, but here 0 is the 0 matrix with the same size of A, right? Partial derivative of some constant alpha multiplying with x is equal to alpha times the derivative of x. And the partial derivative of x plus 1 equals to partial x plus partial y, right? Partial trace of x equals to trace of partial x, and all kinds of stuff. So there's a great reference book called Matrix Cookbook, which is free online. And the common recipe to compute matrix derivatives is just to check out the Matrix Cookbook. Use that as a dictionary, and then just decompose your original function according to chain rules and reduce to the conclusions listed in the Matrix Cookbook, and then just combine them together by those rules. Okay? Any questions so far? Great. So now we have finished a quick review of the basic knowledge. Hopefully that will help you to stimulate you to record some things, some knowledge which you have learned before. Right? So next we're gonna start our machine learning. Right? Well, I will switch to our slides. Okay. So can everybody see this? See the new slides? And can everybody see the smooth transition of the slides?
Yes.
Yeah.
Okay, great. Okay. And next, we're going to first introduce the general framework for supervised learning, and then we discuss the representation of our first machine learning models called decision trees. Right. So first, what is supervised learning? So we have briefly discussed about what is supervised learning, right? So basically, it's like as an analogy, right? As human beings, we want to say supervised learning is like you have a teacher, right? And when you solve problems, the teacher will provide you the answer, and according to the answer, you're going to improve the capability to solve the problems. So in machine learning, it basically means that okay, I can show you an example and also the answers, and then you can utilize those examples and answers to gain the capability to solve new problems. Let us to give a concrete example. Let us look at the running example, right? So suppose our task is to automatically classify news articles, right? So you have a lot of like news articles. I want to categorize them into different classes, right? Say one piece of news article, we consider it to be a sports article, right? So that means we tag a label sports on this particular article, right? So of course, we might to tag a lot of articles, right? We have many articles generated every minute from online, right? Or from newspapers, right? So also we have a set of interested tags, right? Or interested labels which you want to tag those articles, right? So and naturally we can view all the possible news articles we want to classify as kind of instance space, right? Which consists of all possible news articles, right? And also, we need to define which set of labels we want to tag. Right? So, for example, if you're only interested in looking to classifying sports, business, politics, and entertainment articles, right? And then we define our label space as 4 labels, right? And then given those instance space and label space, our task, our machine learning task is essentially to find a mapping, which maps each news article in this instance space to a specific label in the label space. This is a whole, task definition for our supervised learning, for our learning. So formally, if we want to conduct a supervised learning task, we need to define the so-called instance space, namely the set of examples that need to be classified or predicted, right? And also we need to define a label space, which consists of all possible labels we can predict. Like, for example, if your task is to classify, to filter spam emails, right? Then your label space will be just binary, right? Spam or not spam, positive, negative, and etc. Right? And then our underlying assumption is that there is a target function, y equals to f of x, which can map each instance in an instance space to a particular label in the label space. And the goal of learning is to find out this target function or find a good approximation to this target function. So, of course, if you want to find this target function, we need to define the range to find, right? Some amount, we need to define what kind of functions are likely to be the target function, right? So essentially learning is a search procedure. It's a search over candidate functions or function families. Okay? And then how can we conduct search, right? In addition to defining what is the candidate set of the functions, right? How can we fulfill the search, right? How can we do the search, right? We need to say examples of the function input and function output, meaning the labels. In supervised learning, we call this training data. So training data are essentially pairs of the instances and the labels, which are generated by this target function. And we need to first collect a set of labeled training data set, and then we feed this training data set to our learning algorithm. And we expect that those training data set will guide our learning algorithm to search over the family of the functions, and then return a best one. The best one is called a learned function G, which is also mapping from the instance space X to the label space Y. And then if this learned function G is very close to the target function F, we can say, okay, this learn is quite successful, right? And ideally, we would like our G to be the exact same of F, but we'll see that it's in practice is really infeasible. So this whole things like instance space, label space, target function, label training data set, and a learning function defines the protocol of supervised learning. So any questions so far about this general framework of supervised learning? Everybody's comfortable, right? Okay, great. And if we can change this learning protocol a little bit, then we actually come to another set of learning tasks. For example, what if I just get rid of all the labels? If I get rid of all the labels, I can only feed the learning algorithm a set of unlabeled training data. And if our learning algorithm can still return a mapping from the input space to some label space, then we call this learning as unsupervised learning.
It's still unsupervised if we provided the label space, but just not associate them with like in pairs for the training data?
Yeah, the label space does not mean supervised. Label space just mean, okay, what kind of labels you might predict, right?
So it doesn't have to make up labels. It just has to figure out how it wants to assign the instance space to the label space.
Yes. And actually on unsupervised learning, people usually won't pre-specify the label space. And it's more frequently that the learning algorithm will automatically define or find the label space. Like imagine you're doing a clustering, right? You imagine doing cluster, you actually do not know how many clusters do you actually have your data set, right? So if you have 2 clusters, then your label space can be 1 and 2, right? You map each instance to be in cluster 1 and cluster 2, right? But they have 3 clusters, then your label space can be 3, right? 1 to 3. So in that kind of scenario, you don't need to designate a label space beforehand. You can just run an algorithm, and the algorithm tells you, okay, you're gonna have like 5 clusters, and I can map each input to one of these 5 clusters. Then your label space will be will have like 5 labels, right? Does it make sense?
Yeah, that's pretty cool. Thanks.
Okay, yeah, and we can also feed our learning algorithm a set of mixed label examples and non-label examples. Then this becomes semi-supervised learning. So you can see all those learning protocols share the same kind of foundations, like we need to have like instance space, we have label space. We assume there's some unknown target function, right? But when the form of the training data are different, it reduces to different learning protocols. Okay. So now let us go back to supervised learning, right? Suppose we have run our algorithm to get a learning function g, right? And how can we evaluate if this g is good or bad? Intuitively, we can just compare g and f, right? If g and f are exactly the same, then we win, right? We have successfully or exactly learned the target function. But in practice, this is always infeasible. Why?
We don't know what f is, the function.
Yes, exactly right. If we know the target function, why should we bother to run some supervised learning and we have to collect training data, right? We just use this target function to prediction, right? To predict, then we're done. So in practice, it is often the case that we can access the output, the function value of this target function, right? As some set of inputs, but we never know the explicit form of this target function. And then how can we test if our learning function g is good or not? Any suggestion? Any proposal?
You have a set of labeled data and instances that you use to see how good your function is, see how many it matches correctly.
Yeah, right. That's how we evaluate in practice. So basically, we draw test examples from our instance space, and we just compare the ground truth label with our prediction, right? If for many test examples, our predictions are consistent with the ground truth labels, that indicate our learning is successful. Otherwise, we still need to improve our learning, right? Yeah, we apply the model to many test examples and compare to the target prediction. So now another question will be, suppose we have pre-collected a bunch of test examples, right? We want to use that to evaluate our learning function. And then can we use those test examples during training?
No, of course we cannot use, because if we use the function, we'll get fit to the tests. So if we have new tests, it wouldn't work well.
Right. It's just like cheating, right? Like human taking classes and taking lectures, the teacher won't allow you to cheat in an exam, right? If you cheat exam, we actually do not know whether you really learned something from the class, right? Same thing, same kind of arguments apply here, right? If you apply test example in the training, that means if I can simply memorize all test examples, I can still get to the very high accuracy here, right? But actually, if you simply memorize it, you learn nothing. You have no generalization capability to any other new test examples. Right? That's why in machine learning practice, we can never confound test examples and training examples. This is one of most commonly made mistakes in machine learning practicing. So later, when you develop your own models, when you test, if you find your model is incredibly good, don't celebrate early. I just check first if you have fully separated the training set and test set. Okay. So now let us summarize the setting of the setting of the supervised learning, right? So in supervised learning, we assume the training examples are given as a list of pairs of the instances and the labels. Those labels are given by the ground truth function or target function, right? And this ground truth function is usually unknown and very complex. And the input x in the computer science domain is represented by a feature vector. And because, computer program only recognize numbers, right? Numerical numbers. We cannot directly deal with symbols, letters from newspapers, right? We need to first extract features that can well represent the original instances. And you will see that in machine learning practice, the feature extraction procedure is very, very important. And then, given the training set, the goal is to find a good approximation for the target function f. Right? So you will see that in practice, it is very rare that you can find the exact ground truth function. In most cases, we expected at most we can find a good approximation to f. And finally, the label space actually determines the kind of problems we have. If your label space just includes two labels, then we call your task as binary classification. If your label space consists of like discrete labels like 1 to k, then we call your task as multi-class classification. If your label space is continuous, say just real space, right, then your task is called regression. Does it make sense? Okay, so here's the general setting. So as we'll see, like throughout this semester, I think most time we'll just introduce different learning models and algorithms under the umbrella of supervised learning, meaning that all those models share the same kind of settings. So this is very important to let us to understand the basic setting. Questions so far? Okay. So whenever you want to conduct the supervised learning, you need to figure out the following questions. Right? So first, what is your instance space? Second, what's your label space? Third, what is your hypothesis space? Meaning, what set of functions which you believe that can contain the target function or contain a good approximation of target function. Right? In other words, what functions should your learning algorithm search over? And what is the specific learning algorithm? Right? And we'll discuss a variety of learning algorithms which are associated with different hypothesis spaces. Right? And then how do you evaluate the success of learning, right? And that refers to the definition of loss function and the evaluation metric, and we'll discuss them as well. So here, give a brief taxonomy of different learning methods and also different learning protocols and learning methods, which we have introduced in last week, right? When we walked through the syllabus. And our first machine learning model we want to discuss in detail is called decision trees. Okay. We'll start with decision trees. And here is how we talk about decision trees. First, we'll give the definition, right? What is decision tree representation? Secondly, we'll talk about how to learn or create decision trees from data. We'll talk about the classical ID3 algorithm, which is widely used in numerous applications. And you'll see that is essentially a greedy heuristics. And everybody should be able to implement your own decision tree learning algorithm in the ID3 framework. Right? And later we'll say, we'll talk about the problem of the original ID3. You see that the original greedy heuristic will end up a very large, deep trees, right? Which is not good. And we'll introduce the concept called overfeeding. And you'll see that overfeeding is bad. It's bad in real world applications. And we should avoid overfeeding, meaning that we should control the scale of your trees. And then that reduced to several variants or extension of the ID3 algorithm, tree learning algorithm, and we should talk about some pruning strategies, like how do we cut branches of the trees to control the scale or control the growth of the tree, and if there are any splitting principles to generate trees, etc. Okay, so before we talk about decision trees, right? We need to know why decision trees, right? Why should we talk about decision trees? What's the motivation, right? So first and foremost, it's very simple and intuitive. You see that decision trees are essentially a set of rules, right? So it's very like how human beings classify problems and predict these situations, right? When we look at a lot of like things happening, read books and data, like we have come out some kind of rules, right? We want to describe a set of rules, and according to the rules, we give different decisions and predictions, right? So decision trees actually are doing this kind of things automatically. And also, the rules are highly interpretable, right? I can output decision trees a set of rules, and you can check whether this rule is meaningful, right? It makes sense, right? And what kind of knowledge this rule reflected, and which we do not know, right? This is very important for knowledge management. And also, although it looks simple and intuitive, the decision trees can be very strong classifiers. And we can use a set of ensemble learning strategies like boosting random forest and gradient boosting trees to build up a forest of decision trees, which are very powerful. And decision trees, finite decision trees, are actually very widely used. More widely than you think, right? It's actually not everywhere. I mean, not every application need to use deep neural nets. Actually, deep neural nets, the application of deep neural nets are restricted to a very small domain. In many other applications, especially when you have noisy data, you have a scarce data, and then you need high interpretation, and then decision trees will be the first choice. Okay, any questions so far? Okay, so in the remaining a few minutes of this lecture, we'll give the definition of a decision tree. So, so what are decision trees? So first, it is a hierarchical structure. The hierarchical structure that represents the data, training data, with a divide and conquer strategy. So you can view it as like root node of the tree represents the whole data set. Then each children nodes represent a subset of data. And each node, in the meantime, is associated with a test feature. So when we grow the tree, we just use this test feature and look at every distinct value that test feature can take. And according to the values each example take in the subset, we can further partition the data subsets into another smaller sets of the data points. Then we grow the tree and we create new nodes, and until we stop. And the nodes at which we stop are called leaves. And only at the leaves of the tree, we give the label of the class we want to predict. And also, this leaves, as we just said, right? As I just said, is a point to stop the partition. So this is just to give you a general definition of the decision trees, right? And we'll see a concrete example, right? So the general idea of decision tree learning is to construct a decision tree that represents our collection of training examples. So let us use 2 minutes to build decision tree from this simple set of training examples. So our task is to classify a set of shapes, right? Circles, rectangles, triangles, and all those shapes has two attributes, namely two features. One is shape, right? One is color. Right? So let us try to manually build a decision tree to hierarchically represent this data set. So before we do this tree, right, we can take a look from this tree, from this data set. Suppose we're given a test case, which is right triangle. Which label should we give for this right triangle?
Label B, maybe, because the B category is the only category that has red items inside it. So it has the triangles inside it.
Yes, exactly, right? Because all the red ones, right, all the red shapes, right, no matter what actual shape it has, they all belong to label B, right? So given a new red triangle, we can label it as B. So we see how it is reflected in our decision tree construction. So we know that we have like two attributes for each example, color and shape, right? We can start with color, right? So our root node, remember, it represents all the examples in our data set, right? And we associate a test feature, which is called color. And then we look into how many distinct values of the color, right? We see we have like three colors, red, blue, and green, right? That means we can grow three branches, right? Blue, red, and green. And then we can partition the examples accordingly. Right? For blue shapes, we can first look at red shapes, right? We can look at red shapes. They consist of like two circles and one rectangles, right? But they are all labeled as label B, right? That means the label is pure. It is subset. Then we can stop growing. We reach at the leaf node. Right? And then we look at blue shapes, right? So in blue shapes, we can say we have like two blue circles, which are labeled as C, two blue triangles, which are labeled as B, and one blue rectangle labeled as A. That means the labels are still diverse, right? That means we can still partition the subset, right? Partition the blue shapes, right? And this time we're gonna use the attribute about shape. We have three types of shape: triangle, square, and a circle, right? And then we can look at, after partition, what are the labels for each subset, right? So first, for blue triangles, they all belong to label B, right? Then we can stop. We end up with a leaf node, and we set the label of this leaf node to be B, right? And for blue square, we say we only have one blue square, which is labeled as A. That means we can stop and end up with a leaf node with label A, right? And for blue circle, we say they are here, right? They are uniformly labeled C, so we stop growing and we end up with a leaf node with label C. And similar procedure can be applied to green shapes, right? So for green shapes, we have two possible labels, right? And then we further partition the green shapes according to their actual shapes, right? Square or circle, right? For green squares, they all labeled as B, so we stop growing. We end up with a leaf with label B. And for green circles, they are uniform labeled as A, so we stop growing, we end up with a leaf node and labeled as A, right? So now we have constructed the tree, right? So you can see this tree is actually a hierarchical representation of whole data set, right? So root node represent the whole data, and the intermediate nodes represent a subset of data, and then until the leaves, right? Each leaf represents a set of data points which has a unique label. So the next question is that, given this tree, how can we do the classification? If you are given a new shape, can we use this tree to make the prediction or give the label of this new shape? How can I do that? Any idea?
So I guess you could start at the top of the tree and simply work your way down in log n time. So
Yes, exactly, right? It's very intuitive, right? We can just look at the attributes of the new shape, and starting, remember, because each node from root to leaf are associated with some test features. We can just going top to the bottom, right, until you find some leaf, and then you report the label associated with the leaf as our prediction, right? Suppose for the red triangle, and we can look at the color, it's red, and then we reach the leaf node, which has the label B, right? Then we predict the red triangle with label B. That's it. Right? So it's it's very intuitive, very simple. Right? But here's one problem, right? Suppose now we are giving a new test example, which is green triangle. Right? How can you get a label based on this tree?
We just have to randomly choose between B and A because there's no real way to decide with this tree.
Yes, exactly. We have a problem here because we cannot find a path from the root to a leaf node that provide labels, right? So for say we can check, right, for green triangle, first you go with green, you come here, right? And then you test the triangle shape, and you don't have any branch that go with triangle, right? So stop here. So that brings the issue, the tree construction issue. We need to ensure the tree construction is complete, meaning that every possible test example can find a path from the root to some leaf node to make a prediction. So we'll discuss these issues on Thursday. And thanks. We'll stop here today.
Thank you.
Thanks.